Hi everyone. Today we will talk about formally discuss uh, division. So far, we have not formally defined division, but today's concept is actually very important because it addresses division from a quite a rigorous um, just perspective. So in school math, you have learned division with quite some just kind of non-rigorous or even incorrect concept, and one of which we actually very briefly discussed, but never went into details. So before we make that point, let's consider an issue that I believe we mentioned in the homework problem. Let's consider this notation. If we say, what does this mean? 5. 13 divided by 5. Your teachers might have taught you will write this as 2, which is the quotient, and then with this R symbol signaling there's a remainder, and we write 3 right there, right? So this is a very common notation in a lot of classroom. And if you have some textbook or homework assignment, you might see this notation as well. But this is very unfortunate because this really does not have much mathematical sense. So we should cross out this. Okay? Why? Because in math, we really need to be very careful and rigorous about anything that we write down. Meaning that in our expression or notation, if we agree with something, then that something can withstand any scrutiny. Why this is problematic? It's because we really cannot tell what is this. What does this mean? Well, if it means something like quotient 2 with remainder 3, is this something well defined? Quotient 2 with remainder 3. What exactly is that? We can easily come up with another thing to get this. Let's just say now we have, say, change the divisor, which is 5 here, to 4. Then if quotient is 2, remainder 3, with 2 times 4 give us 8, plus the remainder 3, we'll get 11. So we can easily figure that if we use 4 to divide 11, what do we have? We once again have a quotient 2, but a remainder 3, right? This can be very easily verified. So let's just temporarily remove the cross out of the first one. Now you see that if this is 1, if this is 2, we have two very different expressions. 13 divided by 5 and 11 divided by 4, they both equal to quote unquote this thing. But in math, once we have this equality, there's a very important property associated with this symbol is that, say, if we have A equals to B and B equals to C, then we must agree A equals to C. What we call transitivity of this equality just expression. So that really is a very important property for what we understood as equality. This is very obvious and intuitive. If A equals to B, B equals to C, then A must also equals C. Then we have a big problem here. So first, we see that 13 divided by 5 equals to, quote unquote, 2R3, a quotient 2 with a remainder 3. But 11 divided by 4 also equals to 2R3. By this property, we will have to agree that now 13 divided by 5 equal to 11 divided by 4. But this is apparently not acceptable. Even though we have not officially studied fraction, but you can clearly see the two are not the same at all. So we arrive at some unacceptable or ridiculous result if we use this notation. The problem here is that what we want from a 13 divided by 5 as an arithmetic operation, we really want it to be a predictable and unique result. That means that we want to get a number. Also, unfortunately, in this case, we will not be able to give an integer as this for this operation, because so far all we know about numbers are just integers. We have not been able to expand our understanding of numbers beyond integers. Also, as a hint, we knew there will be many numbers on the number line in the future when we study, but for now, we only know those integers. So, as the result, this is not something we wanted, because this really represents two numbers, right? One is 2, one is 3. A quotient and a remainder, that's two numbers. And this result, a quotient with a remainder, cannot be our expected result for such an arithmetic operation. Okay? So, in other words, what we want with this arithmetic operation 13 divided by 5, we want a number, a single result. While in reality, we put it as a combination of a quotient and a remainder. So this is inherently impossible or ill-defined. We cannot use this to be a result of 13 by 5 divided by 5. Okay, so that is a very important observation before we discuss. So for integers, which we have that's the only thing that we have so far, how do we understand this operation? A divided by 3. We have notice we have not officially defined this, but with our previous study, we know this, we understand this operation. That brings up a really important question. What is exactly this? And how should we properly define it? Okay, that's what we will have to discuss about today. That is the important concept of division versus what we call division with remainder, which we actually knew what it is, as we just demonstrated, right? But it's very important to understand those two with some rigor. So before we bring up or bring in the concept of fractions, all we can work with just integers. In the context of integers, before we actually just define what a divided b is, we actually have to put a constraint. So this arithmetic operation, a divided by b, by this we really mean this operation. Okay? We will put a constraint on this operation. This operation is meaningful only if a, which we call the dividend here, is a multiple of b, which we call divisor. So what that means is that before we can even make sense of this operation, we need to make sure that a is a multiple of b. What does that mean? What does a is a multiple of b mean? So, well, the concept of multiple, it's actually nothing but a multiplication concept, right? So when we say 2 copies of 4, or 2 times 4 equals to a, then a is a multiple of 4, 2 copies of 4. By the associative property, we can also say a is a 4 copies of 2. Either way, it's true. So we do know what a multiple means. So that means that if we want to check whether a is a multiple of b, that means we need to find another integer that's called m. A equals to m times b. Okay, to make this more consistent, we might want to change this letter. Instead of a multiple m, we may want to change it to another letter q, which actually will, as we will see, represent quotient. So if we can find another integer q, then we can say if a equals to q times b, then we will say a is a multiple of b. One important observation is here, we actually have not discussed whether a or b are positive or negative. So as long as they're integers, as long as we can find such a relationship, this will meet our definition multiple. In other words, if you have, say, negative a equals to negative 4 times 2, we put negative 4, negative a is a multiple of 2. Conversely, it's also true if we have 4 times negative 2, this is again true. We will say negative a is a multiple of negative 2. So whether those numbers are positive or negative do not really matter. Also, for now, for the sake of discussion, we want to pay more attention to positive integers only. So that means that if A can be represented as the product or the multiplication of some integer q of b, then we say A is a multiple of b. So with this understanding, now we look at this division A divided by b. That means that we want to define such an operation only when A is a multiple of b. We will see shortly if A is not a multiple of b, what we can do. But for now, let's just assume when we discuss this particular arithmetic operation, A divided by b, where A and b are both integers, we want to see how we can define that. But we don't want to go too fast, so let's assume for now that both A and b are non-negative. Okay? There's a big constraint, so we don't want b to be 0. Okay? So this is a big constraint. We will shortly see why this is the case. Okay, so now our job is that we want to properly define this operation. There's some integer, positive integer or non-negative integer, which is a natural number A, with this quote-unquote division operation divided by another positive integer b for now. B could be negative, but for now we want to focus on b is positive. But there's a very important constraint, that is b cannot be 0, and we'll see why. Okay? So how do we properly define A divided by b? Remember, we just discussed this. We will have to guarantee that in this case, we will be able to find another integer q so that A actually equals to q times b. Okay? This sounds like a little bit confusing because we have not even defined what this is. Why do we want to check this first? Well, that's exactly because we want to make sure that this is well defined. We want to avoid a case like 13 divided by 5. Because if that's the case, we will not be able to find a result. In other words, we cannot define this properly. So this constraint exists only because so far we only have integers. We don't have anything else. If we don't put this constraint there, we will have the embarrassing situation that we will not be able to define what this is. Okay, 13 divided by 5. So with this understanding now, let's look what A divided by B is. Perhaps we should start with a simple example. Okay, so let's just say we want to understand what is 10 divided by 5. Remember, we define multiplication as repeated addition. Just as a reminder, how do we do that? So if we want to say 2 times 5 How do we do that? Well, that's just repeated addition, right? So it's actually 5 plus 5. So on the number line, we have 0, we have 1, 2, 3, 4, 5. 5 is here. We just count forward because that's just addition. We just add another 5. So we get a 10. This is 5. That's how we actually define multiplication. So the very concept of division is actually based on this fact. If we start with 10, this is 10. We want to know what this is. So in this case, instead of addition, we will do subtraction. Remember, subtraction and division are essentially the same. Okay, subtraction is actually just the inverse operation of addition. So similarly, division is actually the inverse operation of multiplication. If in this context we put this constraint there to avoid something like this, 13 divided by 5. If that condition is met, division will be shown to be the inverse of observation. So because we define multiplication as repeated addition and subtraction is the inverse operation of addition, intuitively we should think that division should be related to subtraction. And that's exactly the case here. So we have a 10, we go this way, we subtract from 10 by 5. And we know that is 5, right? 10 subtract 5 equals to 5. So this is the first copy, the first 5 that we subtracted from 10, and we arrive at 5. So we just subtract 1 5 from 10. But at that point, we will continue. We have 5. We will subtract yet another 5 from 5. We continue subtracting another 5. So we subtract one more 5. What do we have? Well, 5 minus 5 or subtract 5 equals to 0. This is a big deal. 0 is a wonderful number. So, as we see, we have subtract 2 copies in total. Why? Because 1 plus 1 equals to 2. We subtract the first copy, and then yet another copy. We subtract 2 copies of 5 in total. So 1 plus 1, that's 2. So in total, we have subtract 2 5s from 10, and we arrive at 0. That means that we don't have anything left. And that's a perfect number, 0. So in this case, that's exactly what we want. We want arrive at a number that shows that we don't have anything left. We are back to 0. And 0 is a perfect number. So that means that we have subtract 2 copies of 5 to arrive at 0. Therefore, this is our definition of 10 divided by 5. That is our result. We define 10 divided by 5 as the numbers of copies of this divisor 5 that 10 has to subtract in order to get 0. Okay? And we know we can get 0 because we know 10 is a multiple of 5. Why? Because that's our assumption. We actually have pre-verified 10 is a copy of 5. This sounds a lot of circular argument, but it's actually not. Because in this case, we truly have already verified that 10 equals to 2 times 5. And now with this knowledge, everything is so predictable. When we subtract 5 from 10, we know we just need to subtract 2 copies of 5, and we are back to 0. Okay? But that helps us to define what this is. Okay? So 10 divided by 5 is 2. This is just an example. So in general, what shall we do? A divided by B with the assumption that we can actually find another number Q times B will give us back to A. So we will see that if we start subtracting B from A minus B, and perhaps we will have to continue minus another B until we arrive at 0. And we are actually guaranteed to arrive at 0 because we already knew A equals to Q times B. So how many times we need to subtract B in order to go back to 0? We will have to subtract Q copies of B. Why is that? Because this fact tells us that if we start at 0, Q times B is multiplication. Multiplication just repeated the addition, meaning that starting from 0, we will have to add B, add B, add B to perform that exactly Q many times to arrive at A. We will have to do this exactly Q times to arrive at A. So now we are doing nothing but reversing this process. We start from A, we subtract B, and we do Q times. We will go back to our original point, which is 0. So that means that our definition of this particular arithmetic operation is nothing but repeated subtraction. Notice that this is exactly the reversal or inverse operation of what we do with multiplication. Multiplication just repeated addition, and in this case, division is just repeated subtraction, with a big assumption that we will do this perfectly. We have already verified that our dividend indeed is a multiple of the divisor. And that's a big constraint. Without this, we will not be able to properly see what this is, because it will never give us back to 0. Unless you try it, right? Subtract 5, we get 8. subtract another 5, we get 3. Subtract another 5, we will get negative 2. We just crossed the origin 0. We will never get to that point 0. So, and a negative number pop up. Okay? So that means that we will never be able to arrive at an integer. Okay, so now we perfectly understand why we need to put this constraint. We have to first verify that the dividend A is a multiple of divisor B. Okay, so now we have 2 questions remaining, and both are important. First, why we put the constraint B cannot be 0, which is very important. The divisor B can never be 0. And second question is that, what if A is not some integer copy of B? And that is, how do we handle this? Okay, so the first question is quite intuitively understandable. If we have 0, say 5 divided by 0, remember we need to verify whether the dividend is a multiple of the divisor. So we have to find some number q times 0 equals 5. And this is impossible. Why? Because we have a 0 here. No matter what q you try, you will never get to 5. Okay, so we know this is impossible. 5 will never be a multiple of 0. Therefore, this will not have any meaning in the very first place, because we want to make sure that the dividend is a multiple of the divisor. Well, so when you have a divisor 0, you will never succeed. You will never succeed. So why don't we just exclude this heads on? We cannot have divisor 0 because we will never be able to verify the dividend is a multiple of the divisor in the first place. Remember, this is still within the constraint that we only deal with integers. Later, you will see that even we get rid of this, even we can work with fraction, the divisor still cannot be 0. But for now, it's very clear. If you have divisor 0, this will always fail. So why don't we exclude this from the very beginning? The divisor cannot be 0. Now, the big question, the second question, is that what can we do, or what will happen when this assumption is failed? What can we do? Well, that brings up our headline or topic issue. So read this slide. We say division versus division with remainder. Okay, you may have already learned this term, division with remainder, but exactly how that works, or what does that mean, division with remainder? So it's very important to understand that as far as integers are concerned, division and division with remainder are 2 separate concepts. Okay, division is what we mean by this operation. Okay, and this is meaningful only if we can verify the dividend is a multiple of the divisor b. And by multiple, we mean we can find another integer q times b equals to a. If we can find such a q in the first place, then this division operation is meaningful. Otherwise, it's not meaningful. We cannot even define that. Now, when this failed, we will have to get rid of this concept of division, and that's exactly where we can have the concept of this division with remainder operation. Notice that it's a different operation. We cannot emphasize this enough. Division with remainder is a different operation from division. They're related, and we will see why. But for now, let's emphasize this. Division with remainder is a different operation from division. Okay, so what is division with remainder? Well, we will have to see why do we need it in the first place. Remember the example we just used? 13 divided by 5. What happened? Well, we tried the way we use for a perfect division. So we subtract 5 from 13, we get 8. And then we subtract another 5 from 8, we get 3. And that's where bad things happen, right? If we subtract another 5 from 3, what do we have? Well, we know at this point, we know we will get -2. But that's something weird. This is -2. Remember, for now, we want to focus on positive integers or natural numbers. So -2 is surely something outside our discussion. We don't want -2. We want to have something within our constraint, that is natural numbers. So when this happens, when we hit the 3, we already reached our limit. We can no longer proceed. Otherwise, the next step will bring up a negative integer. And that's exactly what we mean by division with remainder. So at this point, we have checked two things. First, how many copies of 5 we have already subtracted from 13? 1, 2. So we have 2 5s that have been subtracted. At the same time, we have something remaining, and that is 3. And we actually call this 3 the remainder. So 2 times 5 plus 3, that equals to our original number 13. So now we know 13 is or can be represented as 2 times 5 plus 3. Agree? This fact really tells us that if we want to do something like this, we will end up with 2 numbers. First one is 2. That's the maximum number or next number of copies of 5 that we can subtract from 13 before we will hit the dangerous territory of negative numbers. So next maximum number of copies of 5 that we can subtract from 13. And after this, we still have something remaining. But at that point, we cannot proceed. Otherwise, we'll go into the negative territory. So that's exactly what we need. So a division with a remainder operation is an operation that will give us not just one, but actually two numbers. One is what we call, as you know, this is the quotient, which is 2, and this is the remainder. This is 3. But even we understand this perfectly, for the reason we already discussed at the very beginning of today's lecture, we cannot, or we should not, write 13 divided by 5 as something like 2 or 3. We already discussed why. Because this notation is yield defined. Otherwise, we will have something like 11 divided by 4 equals to 13 divided by 5. And this at the same time, meaning that this operation cannot be valid. Because we already say that this is only meaningful for the case where something like 13 is a multiple of 5. Now we see that 13 is not a multiple of 5. So we should not use this notation or this expression in the first place. So how do we actually represent this idea division with remainder in the first place? How can we actually express this operation? Well, good news is that it's something that you have already seen right here. The bad news is that this is a little bit confusing. So when we say division with remainder as an operation, actually the correct way to show this is, guess what? We will have to use this expression to tell the fact that we are doing division with remainder. So this is actually exactly what we need to express the idea division with remainder. Okay, so 13 divided by 5, in this case we can verify that 13 is not a multiple of 5, and it will have to be presented as a division with remainder expression or operation. So the correct way is just write 13 as 2 times 5 and plus 3, where we know 2 is just the quotient and the 3 is the remainder. In other words, whenever we encounter a case where the dividend is not a multiple of the divisor, we will have to resort to the division with remainder operation, and that will have to be represented in this fashion. The original dividend will be represented as a quotient times our divisor 5 here, then plus the remainder we will see. Sounds like interesting because this is something we already knew. That's right. We already know the right-hand expression. But in this context, we use this to represent the very operation of division with remainder. Okay, so in this case, we can summarize what do we do with division. So we have to break this into two cases. So we want to discuss the case A divided by this concept B. What do we know about this? Well, we first have to verify whether we can find a Q such that A equals to Q times B. If yes, we go to the first case, that is A divided by B. We use this notation, this symbol, A divided by B. And we know this will give us Q because we have already verified that. And the precise definition is that we want to repeated subtraction by subtracting B, and we know by performing this Q times, we'll go back to 0, and that is why we can define this way. We have already pre-verified this will be the case. So this is the first case. If A is a multiple of B, this concept A divided by B will be represented this way. And the second case is obviously if this failed, we cannot find a Q multiple for B, then we will have to go with the division with remainder operation. And that is actually represented as this Q. We still have a Q. That's the maximum times of copies of B that we can subtract before we hit the negative territory. Q times B plus a remainder. So pause for a second to carefully look at this division with remainder format. Can we make some comments about this? Yes. There's a very important fact about R, this remainder. And what is it? First, R has to be non-negative, right? That's what we have repeatedly emphasized today. This is a scene that remains before we hit the negative territory. So R cannot be already negative. So R will be at this equal to 0 or non-negative. But wait a second. In this particular case, R cannot be 0 because R is 0, then this will go back to the first case, right? If R can be 0, then we actually could verify that A is indeed a multiple of B. So R cannot be even 0, so R has to be greater than 0. That's one thing. At the same time, can R be greater than B? Or can R be equal to B? Either way, if that's the case, we can continue to subtract B from this operation, right? If R is greater than B, we can subtract another B, and we still have something remaining. And if R is exactly B, we can still subtract B. And worse, that in that case, we'll have perfect division. And once again, in that case, we will have to go to the first case. But we already know that we already tried that. We failed. That's where we are. We are discussing the case A is not a multiple of B. So that means we have to have this condition. R is actually less than B. So combine those two together, we came up with this conclusion. R, the remainder, has to be strictly smaller than the divisor B, and in this case, remainder has to be positive. That's why we have a remainder. If remainder is 0, then we will actually go back to the first case. So in this second case, where division with remainder is at least 1, but it also must be smaller than divisor B. And that's why we call it a remainder. There is something concrete there. It cannot be 0. And this remainder cannot be too big, cannot be bigger than B. So that's what we have with this concept, what we mean by dividing A by an integer B. For now, both are natural numbers and B cannot be 0. Okay? So, in summary, when we deal with integers, when we deal with division, we have to be very careful. We have to branch out into two cases. First case is that the dividend is actually a perfect multiple of B. In that case, we use this notation or this operation symbol. That means that this makes sense in the context of integers. We have to emphasize everything discussed so far is with the constraint that we are dealing with integers, because that's the only thing we know. We will see this symbol can remove this constraint if we have already expanded our understanding of integers. In fact, this is the chicken and the egg. The very reason we need this constraint is because right now the numbers we have are only integers. Therefore, we have to put this constraint there. So if this constraint is not met, we have to go with a separate second operation, and that is called division with remainders. Now, we mentioned that the two operations are related. Division and division with remainder are related. How do we connect them? How do we relate them? Well, that lies in the case, what if R equals to 0? We just say that R cannot be 0, right? The remainder cannot be 0. So if we think that R equals to 0, what happened? 0, you add 0, that doesn't do anything. So this 2 case becomes A equals to Q times B. And that is exactly the condition that we want to meet for the first case. Therefore, we see that the first case is actually just a special case, or at least we can think that way. The first case is just a special case of the second case. And that special situation occurs if R is 0, or at least conceptually we think that the remainder is 0. If that's the case, the second case will have to become the first case. So in other words, if we relax this constraint, r has to be greater than 0, if we do allow r to be 0, then we can actually unify the two situations into one, and that is, this is general case, a equals to q times b plus r. Now we relax the constraint that r has to be positive in order to include the first case, so that, but remember, strictly less than b, that is still required. So if now we relax this one, so make it clear, we put this into a green color, notify this is that this is actually a relax of this. So if we have this, then we fold the first case into the second case. In other words, this version of the second case is more general than what we have here. It includes the first case. Okay, so make sure that we are not confused here. We proceed very carefully about our wording and notation, everything, to make sure that we do not have some inconsistency here. This is not second case. This is a relax of second case in order to include the first case. So now we unify case 1 and case 2 into this general expression, a equals to q times b plus some remainder, but this remainder can be 0. And remainder, if 0, then this is actually a equals q times b, and we know in this case we can use this division operation so that a divided by b equals q. And this last expression turns out to be an extremely important concept in mathematics, and we call this the division with remainder theorem. Okay, so for now, this actually can be broadened to negative integer for actually a and just a and d. But for now, we limit ourselves to positive integers only. Actually, a can be 0, but that's a separate issue. But this version of the theorem says that for any natural numbers, remember that includes 0, a and d, but d doesn't equal to 0. So that means that only a can be 0, but d has to be positive. So for those two numbers, any natural numbers, a and d, as long as d is not 0, there exist unique natural numbers. Okay, so this word qualifier, unique, is very important. There exist unique natural numbers q and r, so that a equals q times d plus r, where r is greater than or equal to 0, but strictly less than d. Okay, this is a very, very fundamental result in math. This is the starting point for a super important branch called number theory. And there are many other names for this result. This can be called the division lemma or division algorithm, or there's a very special name for it. It's called the Euclidean algorithm or the Euclidean algorithm, lemma, because this actually just first recorded discussion is in ancient Greek mathematician Euclid's just a masterpiece Elements. Okay, so this is actually the foundation for very important algorithm called Euclidean algorithm. Okay, so let's repeat this one more time. For now, we limit this to natural numbers. So if we have two natural numbers a and d, where a is actually the dividend and d is the divisor, but we are not talking about this. We are not talking about this theorem in the context of division. We just want to say if there's a, if there's a d, and d is positive because it's a natural number, it's not zero, so it's a positive integer, then a can be represented in this way. Q is some natural numbers. It could be zero, but there's some Q there, and it's unique. Q times D plus another unique non-negative integer or natural number R. So A can be represented as Q times D plus R. And R is strictly less than D and non-negative. You may question, how do we find Q and R? Well, that's what we have spent the whole lecture to discuss this, right? This is just by repeated subtraction. We start from A, we subtract, in this case, a D, a divisor, from A, then keep doing that until right before we go into negative domain. Okay, if we go into the negative territory, then we overshot. So we have to go back before that last step and count how many times we have subtract this D from A. And that number, how many times, is our quotient Q. And then after this last step, we will have a remainder. And this remainder we know is non-negative, but it can be zero. If it is zero, then we have actually a perfect division. So this will be actually A equals Q times D. That will be our normal division. But in general, we will have some remainder, and this remainder is strictly less than the divisor D. Okay, that's how we find it. So you just repeat subtracting this, and this is called division with remainder. Once again, this is an extremely important result, and it also embodies an operation, what we call an algorithm. It's a procedure that we can follow, and this procedure will allow us to actually find this Q and this R, the quotient and the remainder. Okay, I cannot emphasize how important this result is. This gives us the very basis for defining what division is. And you will see later that when we study some basic number theory, this gives us all kinds of possibilities of like finding the factors, the common factors, the greatest common factor, what we call GCD, and so many intricacies. This is the foundation for mathematics. Okay, so we'll stop here. I hope you did not get confused by today's topic. It's very deep. Let's just admit it. It's deeper than what you would learn as a fifth grader from your school math. But it's very important to understand division with remainder is different from division. Division should give us a single number as the result, while division with remainder is the result that we know that cannot happen. We cannot just get a single number to meet our goal. We have to come up with two numbers. One is the quotient, one is the remainder. By the way, we will have one more lecture because of all the because of my illness. We are a little bit behind, but this is a free class, so we will have another lecture on Friday, and then we'll have Christmas, right? So I will see you on Friday. Thank you. Bye.